So today we're going on and continuing the course, and we're going to be starting off with systems neuroscience, in that we're going to be discussing sort of our first system. And so in terms of the lectures, I find that this is one of my favorite lectures to teach because it's sort of integrating everything and really getting into the neuroscience perspective and understanding how it works in unison for a particular function. This system that we're going to be discussing today is the somatosensory system. And so if we wanted to understand how our body moves, we needed to first be aware of the machinery and the different components and how structurally they work functionally. However, what up, Eric? However, today we're getting sort of an understanding of how the system works, or sort of how the system works for a particular function. Does that make sense? Yeah, so the motor system is the next lecture. So there's three. So Hannah, which three systems travel through the different levels of the central nervous system or the neurological system? So remember how there was like the sensory system, the motor system, and the autonomic system that will run through all levels of the neurological system, so central and peripheral. Yeah, so today we're starting off with the first one, which is the sensory system, or the somatosensory system. And it's interesting because we're going to get a breakdown of how our sort of sensation ability is broken down and what that means, sort of looking at it from a neurological level. Was there any questions from the asynchronous lecture? No questions? Okay, perfect. Because if the point of this course is to understand from a neurological perspective how we move, then understand that to make a coordinated voluntary movement with a purpose, we need to be aware of our surroundings. So in terms of like sort of the cycle of movement, sensation, or the somatosensory system, is first. If we're aware of our surroundings, then we can initiate a movement that is coordinated and specific. So the first step in us moving properly is being aware of our surroundings. And that's going to be through the concept of sensation that we're going to be learning about today. So we went through the asynchronous lecture, and you went through sort of understanding what somatosensation is. Up to the point that we perceive the sense, it's just an electrical signal. It's how our brain perceives that sensation, is how we sort of consciously perceive the sensation. So that's the process of somatosensation. Our sensory information starts off from the dendrites of our sensory nerves with specific sensory receptors. You may have, Jennifer. Did you remember all this? Talk about receptive fields, the different receptors in each of which this is the right lecture, no? So then, wait, so Jennifer, do you never do the asynchronous lectures? So then which one did you do this week? It wasn't this one? Which one did you do? Oh, yeah, there's always one before the synchronous lecture. Well, no problem. Yeah, you can just do it right now. Yeah, so we have a question talking about alpha gamma coactivation. And so alpha gamma coactivation is very important in terms of maintaining our muscle spindle sensitivity. Our muscle spindles are going to be the sensory receptors that are involved in our proprioceptive sense, or our sense of awareness of body positioning. Now, they act like a tape measure, or like a any sewers when you have the ruler, but it's like movable, like a string. To register length, you have to make it tight so you can register the length of the fabric. Our muscle spindles are like tensioning elastics in our muscle fibers. So they register changes in length by getting pulled and stretched when the muscle lengthens. If we shorten the muscle, we also have to make sure that we shorten and keep the muscle spindles tense, or else they can't register length. So what happens is that when we send out a signal from our motor cortex areas to the muscles to contract them, we also reflexively at the same time contract our muscle spindles of that muscle using the gamma neurons, which go to the muscle spindles. The alpha neurons go to the muscle fibers. So when we send a signal, they both activate at once. So that way muscle spindles contract when muscle fibers contract. And it maintains the tension in the muscle spindle, and therefore it can register muscle. Does that make sense, Emraj? Perfect. Okay. Manine has questions. Yes. So they have different receptors. So the Golgi tendon organs and joint receptors, they register just tension. So for the Golgi tendon organs, you notice them at the end range, right? Whereas muscle spindles are registering length throughout the full range of motion. Joint receptors are even more. So that when there's tension, then you get the tension in the tendon, then the tendon receptors would be giving information. And at the full end range of motion, that's when the joint receptors would start to get tensioned, and then they would send information. Does that make sense, Bunny? Awesome. So I want you all to break out a piece of paper, and on this piece of paper, here, I'll do it with you guys. Shammy, can you bring me a clipboard with 2 pieces of paper and a pen? What I want you to do is to write on the piece of paper. I want you to write 1, 2, and 3. I want you to write the conscious relay pathways, the divergent pathways, and then under 3, unconscious relay pathways. We're always going to be referring back to this slide because these are the somatosensory pathways up to the brain. So going from receptor up the sensory neuron to the spinal cord and up to the brain is going to travel through one of these 3 pathways. These 3 pathways are all sort of neurons grouped together for a specific purpose. So let's first talk about the conscious relay pathways. It's these pathways that are going to end up in the somatosensory area that are going to be for conscious discriminative sensory perception. Come on in. Don't say hi. You don't say hi. She's scared. She's nervous. Thank you. So 1. Conscious relay pathways. 2. Divergent pathways. And then 3. Unconscious relay pathways. Okay? 1, 2, 3. Everyone got that? Because we're going to keep referring to it throughout the course, or throughout the lecture, sorry. So let's first talk about the conscious relay pathways. This is going to be giving our 4 conscious touch sensations of touch, proprioception, pain, and temperature. Sorry, our 4 conscious perceived senses of touch, proprioception, pain, and temperature. Now, there's 2 systems that we're going to learn in the conscious relay pathways. they both end up in the somatosensory area of the brain where we convert electrical signals into our sense. They are both going to utilize 3 neuron pathways. So that means that from the receptor up to our brain for perception, it's 3 neurons. The less neurons, the faster the system is, right? Because then it doesn't have to synapse as many times. So 3 neurons is pretty quick. What's going to happen is we're going to learn about the 2 different pathways, the dorsal column and the spinal thalamic tract. They both provide different types of senses, but they're the same in that they end up in the somatosensory area and they use 3 neurons. Yes, but proprioception can happen consciously. So if I close my eyes and I get someone to move my arm, I have a sensation of where my arm is in space. Does that make sense? To be consciously aware of the sense, it needs to end up in the somatosensory area. So I can have conscious perception of pain. Let's say I stab myself. I know where that is because it's ending up in the somatosensory cortex. I can feel cold. If I feel like a cold test tube, but I feel it in my hand or my foot, I can be aware that that's happening because I have that sense going up into the somatosensory area. And it's discriminative, right? Because think of like the homunculus. We're aware of where that's happening in our body. These 2 systems that are part of the conscious relay pathways, they use 3 neurons. So we have the first neuron that goes receptor up to the spinal cord or medulla. The second order neuron, the second neuron crosses over and goes to the thalamus. And then the last neuron goes from the thalamus up to the appropriate part of the somatosensory area. So if it was the foot, it would be the inside. If it was the face, it would be more on the side. Okay, so do we sort of get that? We're going to be talking about the conscious relay pathways. That's going to be for conscious perception of our senses. We have 2 different pathways that provide that information. We have the dorsal column 1 and the spinal thalamic tract 2. And the difference between these 2, the main difference is the type of sensation that they're providing. So on our sheet, conscious relay pathways, divergent pathways or medial divergent pathways, and then the unconscious relay pathways. We're going to write under conscious relay pathways, 1, dorsal column, 2, spinal thalamic tract. Has everyone done that? Perfect. So it's through these 4 senses. Kyle, you're just going to write down the dorsal column and spinal thalamic tract under the conscious relay pathways. Being able to feel these senses is going to be important for us to discriminate what objects we're manipulating. So that process of being able to understand what's in your hand, everyone take your hand out, close your eyes and put a pen in. You can feel very quickly that it's a pen. If you put a key in your hand or you put in a key ring or an ice cube, we can feel what's in our hand by discriminating between the different senses. So the interplay of touch plus proprioception, I can understand how my hand is positioned, allows us to integrate that information in the somatosensory area to figure out what shape is in our hand. That process is called stereognosis. And it happens because we're able to use, like Talasi was saying, proprioception, we're able to use conscious proprioception plus conscious touch. So we can make a 3D image or understand what is in our hand. Now, people that have neurological disorders sometimes can't do that. And so a clinical test is to have them close their eyes, put something in their hand and have them feel around. If they can't register what is in their hand without looking at it, there's a problem with proprioception or touch. And in these pathways of that information going up to the brain. So somewhere along the line, there's a break. Does that make sense, everyone? Kyle, you good? Awesome. Okay, good. So let's first talk about the dorsal column. The dorsal column is going to be important for fine touch, proprioception, and vibration. Fine touch, proprioception, and vibration information, so those senses, is going to be transmitted up to the somatosensory area via this dorsal column. It's located, it's a tract of white matter at the back end of the spinal cord. That's why it's called the dorsal column. It's at the back end. It's a column at the back, dorsal column. Now it uses 3 neurons to get from receptor in the skin or muscle up to the spinal cord, up to the medulla, where it crosses over and then goes into past the thalamus into the somatosensory area. Remember how we said that the right part of the brain is responsible for the left half of the body and vice versa, and so that the neurons cross over at some point? So the crossing over for the dorsal column and the spinal thalamic tract, the 2 conscious relay pathways, it occurs in the second order neuron. So we said that both systems use 3 neurons to get from receptor up to the brain. So the first order neuron goes from the receptor either to the spinal cord or to the medulla. The second order neuron goes from the spinal cord or the medulla, crosses over and goes to the thalamus. And then the last neuron goes from the thalamus to the appropriate part of the somatosensory area in the brain, in the cortex. So I just wanted to clarify, do you all remember me saying that the thalamus is the ultimate relay center? So anything coming in and out of the brain goes through the thalamus to sort of relay it to the appropriate spots? Okay, perfect. So then, on another piece of paper, I said you have to have 2 pieces of paper. On this piece of paper, what you're going to do is you're going to draw out what it looks like to have a sense from the skin up to the brain using the dorsal column. So I've drawn a stick man. That's terrible, but I like stick man. Okay. If we have a sensation of what? What does the dorsal column provide? Fine touch, proprioception, or vibration. So we have a sense happening at the foot. The first order neuron is going to go from the receptor. So here's the dendrite. Goes into past the dorsal root ganglion. So it's still the same neuron. Goes all the way up the spinal cord, up to the medulla. So the medulla, remember, right in here. The second neuron is going to cross over and touch the thalamus. And then the third neuron goes to the appropriate part of the primary somatosensory area. So do we all understand how it's 3 neurons? The first one is, look how long it is. It goes from the foot all the way up to the bottom of the brainstem. Very long. Then there's the crossing over. It's always the second one that crosses over, the second order neuron that crosses over. And then the third one is from the thalamus to the appropriate part of the cerebral cortex, the primary somatosensory area. And if you can look at this diagram here, we see that, where we have the first order neuron, so receptors for touch, proprioception, or vibration, coming in to the spinal cord. Here's the dorsal root ganglion. That would be the cell body of that neuron. It goes all the way up, spinal cord, up to the medulla. Then we see that the second order neuron crosses over, right? See it right here. It's crossing over the midline. So now, let's say this was for the right part of the body. It's on the left side of the brain. And then it goes from the thalamus up to the appropriate part of the primary somatosensory area, which, because this was the foot, would be located on the inside or the inner surface of that. Does that make sense, everyone? So remember, the dorsal column is for which senses? So Lassie? No, which senses? The specific ones. Fine touch, proprioception, vibration. Yeah, perfect. And then the second order neuron in this dorsal column is right here. So the first order neuron will go all the way up, right, to the spinal cord, up the spinal cord, into the medulla. Then from the medulla, it crosses over to the thalamus. And then the third neuron goes from thalamus to the part of the cerebral cortex. Yeah, so when it says, so for the dorsal column, because remember, they're all going to cross over. The crossing over happens at the medulla. And the difference is that for the spinothalamic tract, the crossing over happens in a different area. That's the difference between the two, plus the senses it provides. But both have 3 neurons, and both the crossing over happens in the second neuron. Would it cross over at the same part of the tracts in the brain that affect the gyroid? It's crossing even before it gets into the brain, Anna. So the reason why it's called the dorsal column, this is the dorsal column right here. The fasciculus gracilis is for the dorsal column of the lower body. Think of the gracilis as like the muscle gracilis is a lower body muscle. This is the dorsal column, the fasciculus cunatus, or cunatus. Cunatus means hand bone. So this would be the dorsal column of everything from the upper body. But both are on the back end of the spinal cord, and then going all the way up to the medulla. We don't talk a lot about the conscious perception of fine touch, proprioception, and vibration, as well as pain and temperature from the face. That doesn't cross through the spinal cord because it goes through our cranial nuclei. So this wouldn't be on a test, but just know that it's still a 3-neuron pathway, and it's utilizing the main sensory nerve of our face, the trigeminal nerve. So fine touch, proprioception, and vibration of the face would be sensed in receptors in the face, and then get sent to the trigeminal ganglion, then to then cross over, and then go to the thalamus. So there would still be the crossing over at the second order neuron, and then it still ends up thalamus to the appropriate part of the somatosensory area. This wouldn't be on the test or a midterm, but just know that for the face, it's its own pathway because it's above where the spinal cord is. This is a picture of the sensory homunculus, just to give you a reminder of where or what parts of the cortex or this somatosensory area is associated with which part of the body. So if we were going to feel sensations of the foot, it would be here, whereas the face would be more on the lateral side. Now, in the lecture, I've given more diagrams as demonstrating or depicting, they're from the textbook, depicting the same dorsal column. So some people like this schematic diagram, because here we see, so green means upper body, red means lower body, I believe. And then blue means face, based on the diagram from the textbook. But it gives you a schematic of how the neurons. So here we have neuron 1 goes from foot up to the medulla. Medulla crosses over and goes to the thalamus, and then it goes from the thalamus up to the appropriate part of the. Oh, there's Joseph. Since fine touch is AV afferents, would the whole dorsal tract to the medial meniscus have the same fibers? Yeah. So all of the pathways would be the same. Well, so the ones that were of that column. So then pain and temperature, so yes, but pain and temperature, which we're going to learn next, different. understanding the sort of path that the information goes from the skin to the brain is important because it helps us understand why we see clinical presentations of certain things. So here we have, let's say that this is the dorsal column. So here we have someone, let's say they're facing away. Here is the first order neuron. This is the second order neuron, and then this is the third order neuron. So if, let's say, there was a stab wound and the person lost their nerve right here, would they lose sensation? What would be, let's say this is the dorsal column neurons, what would they lose sensation of their foot? Yep. Yep, all three of them. Perfect. And of which foot? The left foot or the right foot? So let's say this is left. Yeah, left. Right? So if you were to get cut or have a lesion anywhere here, you would be losing sensation to the left side or left limb. Let's say there was a lesion here. They would be losing sensation to the left hand. The problem is that if they were to get a stroke or a lesion up here on the right side of the brain, let's say it was affecting senses of like an area of the cortex that was for fine touch, proprioception, or vibration, would it affect the right side or the left side? Left. So the important thing to take from these diagrams is if we know where the information is crossing over, then we can understand why sometimes it would affect one side of the body and not the other. Could you imagine back in the olden days when someone hurt the right side of their brain and all of a sudden they lost sensation to the left? It wouldn't make sense. They didn't understand sort of the pathways of how it sort of worked out. But now that we understand, we can put that in our clinical picture. If you get an injury after the system has crossed over to the opposite side, then it's going to affect the opposite side of the body. Exactly, Joseph. They definitely thought it was witchcraft. So then the next conscious relay pathway is the spinal thalamic tract. So if the dorsal column was for fine touch, proprioception, and vibration, the spinal thalamic tract is for coarse touch, pain, and temperature. Coarse touch is like a tickle, or like, you know, when you like someone touches you and it's like a, like, let's say like your crush is like goes to touch you and you get like a warm sensation. It's poorly localized sensation or poorly localized touch. It's not discriminative touch, so that's why it's called coarse touch. The other things, or the main two senses that the spinal thalamic tract senses, are pain and temperature. So pain is an extremely complex phenomenon, and there's slow pain versus fast pain. We're going to get into this lecture what those two things are, but know that fast pain or localized pain or discriminative pain is transmitted through the spinal thalamic tract. So when I get pain somewhere, I can localize where it is because that sensation is ending up in the primary somatosensory area. As well as temperature, cold and hot, I can understand where that's happening in my body based on this tract. Yes, exactly, Hannah. So I don't want to get too far ahead of it just because I want to go through the pathway first, and then we'll go into the differences of slow pain and fast pain. So now let's talk about the spinal thalamic tract. So this is the second pathway, and again, it has 3 neurons to get from the receptor up to the primary somatosensory area. The difference with this pathway is where the crossing over to the other side of the body happens. So, Joseph, since you've read ahead 17 times, where does this crossing over occur? Perfect. So that's the main difference, in that with the spinal thalamic tract, the sensory information goes from the receptor up to the spinal cord, then crosses over. So the second order neuron is the crossing over at the spinal cord up to the thalamus. And then the third order neuron is from the thalamus up to the appropriate part of the primary somatosensory area. Yeah, so what happens is wherever the receptor is located, so whatever spinal nerve it goes in through, so like lower body is the lower spinal nerves, upper body, upper spinal nerves, the crossing over would occur wherever that neuron is entering into the spinal cord. So let's say it was that leg again, it would be crossing over the lower spine, wherever it is inserting into the spinal cord. It crosses over immediately. Yes. And that's the difference. Whereas with the dorsal column, the evolutionarily newer one, it all went up the spinal cord and then crossed over at the medulla. They all crossed over at one spot. Whereas in the spinal thalamic tract, it's crossing over upon entry. No, dorsal is fast and spinal thalamic is fast. The dorsal column doesn't provide pain. So these will be both registered as quick. Alpha, Delta. Yeah. Do we just make that? No, Joseph just wants to know. Spinal cord. So let's look at this diagram here. In our gingerbread man picture, with the dorsal column, we had the crossing over happening at the medulla. If we had pain from the foot, it would come in to the spinal cord, synapse. So that's the first order neuron this time. The second order neuron is crossing over immediately and then going up to the thalamus and then the appropriate part. So the 1, 2, 3. Does that make sense? So back with what Joseph was saying. So if you go back to the asynchronous lecture, it'll tell you which of the afferents are associated with of the different fiber types. Once it gets into the column itself is one speed. They're talking about the first order neuron, then it goes into the tract, right? So you'll find that the dorsal column ones are faster because the tract is the receptor. Whereas with pain and temperature, see how the first order neuron goes in and then the second order one crosses over? The second order one is going to be the speed of the white matter, where you have the lower speeds in the pain and temperature ones on the initial one. I'm going to confuse everybody, but that's for Joseph. Yeah, that's why. But do you all understand the crossing over difference? Because if we look at this diagram here, with the spinal thalamic tract, see how the first order neuron goes right there? Then it crosses over and goes all the way up. And then the third order one is the same for both, thalamus to the appropriate part of the somatosensory area. And then just like the dorsal column, pain, proprioception, fine touch, and vibration in the face, pain and temperature can also happen, or that sense can happen from the face, but it's using the trigeminal nerve. and it's a different nucleus of the trigeminal ganglion. And then it goes, again, crosses over with a second order neuron and ends up in the appropriate part of the somatosensory area. So how do we feel about that? About understanding that pathway, the differences? We have three different three different pathways that we're going to be learning about today. Remember, the first one is the conscious relay pathways, and we just learned it. So our conscious awareness or our conscious sense is happening through two pathways. The dorsal column, which is going to give fine touch, proprioception, and vibration, and then the spinal thalamic tract, which is going to give coarse touch, pain, and temperature. And that's how we get our senses. If we're going to be aware of a sensation, it has to end up in the primary somatosensory area. That's the area that converts electrical signal to sensation. Okay? So that pain that we're talking about in the spinal thalamic tract, that's localized pain. It's fast pain. Because if I hurt myself, if I close my eyes and this is going to sound morbid, but I pinprick someone, they can tell where that pain is going to, right? Thank you, by the way. And that's because it's ending up right here in the brain, right? So it's here that's telling you where it's coming from. That's called fast pain. Fast pain is the spinal thalamic tract. So when you said that spinal thalamic tract is sending pain information, they're talking about localized pain or fast pain. Fast pain is the immediate and initial sharp sensation or electric sensation, which indicates the location of injury, where you hurt yourself. And it's because it's going to the somatosensory area. Yeah, like when you stub your toe. So, has anyone ever... Well, no, that's different, Karen, because fibro pain is a constant pain. Has anyone ever broken their arm or broken a bone? Think of like something like a very significant injury. You get your initial sensation of, oh God, I hurt myself in this area. And then it starts to throb, it gets warm. Sometimes you go into shock, you get pale, you feel nauseous, you're gonna puke, you get stressed out. All of that sensation. All of that happens after. So that's the slow pain sensation. That's why it's called slow pain. It happens through a whole other pathway. And that is what the medial divergent pathway is. So now we're going to talk about that pathway. So for pain, they're going to be both fast and slow, right? Slow pain isn't localized. So if I have pain right here, in some way, it's going to end up part of it has to end up in the primary somatosensory area. Slow pain is where that pain sensation goes to different parts of the brain and body that aren't the somatosensory area. So you're not localizing the pain, it just happens. Joseph had talked about cross analgesia, and I just want to talk about that here. Because with fast pain or the spinal thalamic tract, because we have crossing over of the neurons or the signal very early, like at the level of the spinal cord, you can get, like for example, a stroke. If you get a stroke in the base of the brainstem, so let's say it's right here, right? It's going to be after pain and temperature neurons have crossed over the midline, but before, because the crossing over of pain and temperature of the face, it goes to the trigeminal nucleus, then crosses over, then goes to the appropriate part of the thalamus. Depending on where the brain injury is, it can be where some neurons have crossed over and others haven't. So you can get this idea of crossed analgesia. Analgesia is loss of pain sensation, right? Analgesia is the absence of pain in a response that should be painful. So crossed analgesia is a clinical term when you have loss of pain from one side of the face and the opposite side of the body. And the only way that can occur is if we had a lesion that's affecting right here. So let's say we're losing pain and temperature neurons. So if it was to be right here, it's going to be on the right side of this diagram. Which part of the body, which side is going to be losing pain sensation? The left side or the right side? Considering the crossing over happens right at the spinal cord. Yeah, it's the left. So even if you zoom in, everyone, and look closely, you can see that the lesion is happening before the face pathway has crossed over. And that's why cross analgesia happens. But initially, they would have been like, this makes no sense. How could that happen? This is weird. This is spirits. They need bloodletting or something. So do we all get that? So now what we're going to do is we're going to talk about the slow pain pathway. This is going to give us all of the sort of like regulatory, autonomic, arousal, withdrawal symptoms associated with a very painful stimulus. So just because Karen keeps asking about it. So think of fibro and MS, or like the pain around those, as pain syndromes. You guys have heard that term, right? Because it's not about slow pain versus fast pain. It's about how that syndrome is affecting our awareness of pain. So it's different. It's a syndrome. This is the system. So this is the system that tells us about our senses. The syndrome is the dysfunction of these. And so with fibro specifically, there is a lot of centralized sort of neurotransmitter release that increases the sensitivity of the area. So for pain syndromes, you get a normal sensation. You feel that as pain when it shouldn't. MS, it would just be if the plaques are affecting a certain part of the pathway. So that's secondary. Whereas fibro, the pain sensation is primary. In MS is the buildup of sclerotic plaques, and wherever they end up, and it could be random, in the central nervous system is going to affect that part. Yeah. So under the divergent pathways, understand this is for the slow pain pathway, and it utilizes a large number of neurons to get from receptor to its destination. So the spinal thalamic tract and dorsal column use 3 neurons. This is infinitely more. So it's a much slower process, but it can have more profound effects. It's called the divergent pathway because we have one signal diverging to a whole bunch of different areas. So it's the slow pain pathway that causes a divergent signal of pain to be sent to different parts of the body, not the primary somatosensory area. So this is to, like, blushing, paleness, heart rate, anxiety, all that kind of stuff. We've talked about substance P as a neurotransmitter. Now, the slow pain pathway is utilizing pathways in the gray matter. I've kind of localized it right here. It's zone 1 and 2 in the diagram. So it is unmyelinated, so it's much slower. And one of the main neurotransmitters utilized in this pathway is substance P. It's the constant modulation from substance P happening that you get like a pain syndrome like fibromyalgia, where you have the neuromodulator being spread all around the spinal cord and up, and it is causing local potentials constantly to, force the neurons to want to send an action potential. So it's increased the sensitivity of those neurons. So then what happens is that you get normal touch sensation because the neurons are already wanting to fire. They're already sensitive. They're depolarized. Normal touch is perceived as pain. Is everyone okay? Promise? Joseph? Lassie? Kyle? Ooh, Jenny. Well, after Jennifer, just email me because you still have to go back and do that quiz. Okay, so under the medial divergent pathways, you're going to write 3 things, okay? Spinothalamic. Oh, sorry. Oh my God. Spinomesencephalic. Do it. Mesencephalic. 2. Spinal reticular. And then 3. Spinal limbic. Okay? These 3 pathways are going to give us our response, our slow pain response to a very painful stimulus. The spinomesencephalic tract, so so this is Latin. So this is where like understanding Latin helps. Remember the spinothalamic tract? It goes from spinal cord to thalamus. That's what they call it that. The spinomesencephalic tract goes from spine to the mesencephalon, which is the midbrain. If we have a very painful stimulus, you've ever thought of the reflex of where, like you hurt your ankle or you're running, you hurt your ankle and you feel it, and then if it's very significant, you turn to look at the pain? That is through the spinomesencephalic tract. It's a reflex going from the, remember the superior and inferior colliculus, that you turn your eyes, the superior colliculus, and you turn your head, the colliculi, the superior colliculi, you turn your eyes towards a very bright stimulus, whereas the inferior colliculus, you turn your head or you towards a very powerful auditory stimulus. This pathway, it sends it to that reflex center. So when you have a very painful stimulus, it will turn your head and eyes toward where you hurt yourself. So very simple reflex. I don't know. Can you think of any situation where you've hurt yourself and and then you're like, and then you start looking at it? Yes, that's exactly why. That's why you're doing it. So that's all that the spinomesencephalic tract does. Have you all ever heard of the reticular formation? So the reticular formation is, think of it this way. So remember the midbrain area. It's for the medulla. It's for the autonomic regulatory processes for homeostasis of our body, right? Yeah, it has like the sleep-wake cycle, all of that. The reticular formation is where we have divergent pathways where if you have one stimulus, it would affect, so if I have painful stimulus, it's going to affect heart rate go up, breathing rate go up, blood flow to my face down because you're going to go pale. It's where we have the inner neurons moving together where it will have sort of a neural network where one stimulus can be divergent to a whole bunch of different areas for regulatory processes. So if this is the neural network for maintaining homeostasis, if we get shock from a painful stimulus where we get problems with our sleep-wake cycle, with our attention, with our heart rate, breathing rate, that's going to happen because that signal is getting sent to our reticular formation. And the reticular formation is going to diverge that signal to different homeostasis parts of our body. So, Talassi, the one thing about anxiety attacks is that there is a cognitive component from the limbic lobe, and that's the next pathway. But the spinal, can we all understand that the reticular formation, so the spinal reticular tract is going to be where we have all of the autonomic changes being pale, sleep-wake disturbances, heart rate, breathing rate, all of that response to pain is because we have a pathway that goes up to this part of the brainstem. Does that make sense? Circadian rhythm is just a term to describe our sleep-wake cycles. So this would interfere with that. Well, so it is sent out there. There's an area that is in terms of like regulating melatonin. Yeah, respiration too. This is the output center. So one signal is going to get sent out effectively to a whole bunch of different areas of the body for regulatory conditions from this network. So it's not about where it's getting controlled per se, it's the output of making sure a signal gets sent out to the appropriate areas of the body. So the circadian rhythm, respiration, we're all talking about different things. That signal is getting sent to the reticular formation, and then that's getting sent out to the appropriate region, right? If I'm tired, I need to, upregulate my digestion, stop my breathing. Like it has to have different things happening, right? Rather than having your brain having to organize what all those is, it's going to take one signal, and then through this reticular formation, appropriately, it's going to be sent out automatically to different areas. Yeah. Anaphylaxis, so an allergic reaction, anaphylaxis occurs locally, so that's a bit different. Yeah. So then Talassi, because you brought it up a couple of months ago. So do you remember what the limbic lobe was for? Right. So the emotional response to a very painful stimulus is because of the spinal limbic tract. The spinal limbic tract is going to make sure that slow pain goes from the painful stimulus up to the limbic lobe. So this is going to be responsible for our emotional response to pain. And so an anxiety attack would be when we have inability because of a high emotional response to deal with what's happening systemically, and then you have an attack. And there are many tracks, which is why I'm making you write down like this. So it's the interplay of, so first there was the spinal mesencephalic tract. The spinal mesencephalic tract is for the colliculi. It just makes you turn your head and look at the painful stimulus. The spinal reticular tract and the spinal limbic tract together are going to create our whole slow pain experience, the whole experience of shock. The reticular formation is for everything in terms of homeostasis and regulatory changes in the body as a result of the pain. And then the spinal limbic tract is going to be for the emotional response to pain. So the response of both, the activation of both, is going to lead to us becoming pale, having our heart race, feeling faint, nauseous, like emotionally distressed, overwhelmed. And then the throbbing sensations. Pain is not local. You can't, that throbbing sensation, it's poorly localized because it's not going to the primary somatosensory area. It's a crude sensation. So explain the question a little bit more specific, Joseph. So you're talking about right here, right? So a withdrawal reflex is movement of the limb away from pain. So no. So see, because they're not going to know, people in the class haven't read ahead, so they don't know what a withdrawal or cross-extensor reflex is, but you're misinterpreting what that reflex is because that's a movement of the limb away from the painful stimulus. That's a interneuron network in the spinal cord. This is like a reflex in that you're experiencing that reflex as a result of pain, except because of this pathway, what's happening is that it's going all the way up to that area, and this causes the head to move to that. So you would have the withdrawal reflex. The withdrawal reflex or cross extension reflex is quick. Let's say I touch a hot pan, and I touch a hot pan, and quickly, and then I can move it. So that's what happens first. Then I'm aware that I hurt myself. Then the slow pain kicks in. Then I look at it. I mean, I wouldn't say it's completely different in a sense, because I get what you were talking about in terms of a reflex. But remember that the extension reflex is at the spinal cord level, so that would be the quickest. Then the signal goes up to the appropriate part of the somatosensory area. That's fast pain. Then the slow pain is the last one. Then that is going to get to the colliculi, where you would look at the area through the spinal mesencephalic tract. So if we look at, does that make sense? Yeah, perfect. So then I like these diagrams because it kind of breaks it down. But look at the difference between fast and slow pain. This is the spinal thalamic tract. See how it crosses over at the spinal cord and comes up? These is the spinal limbic, the spinal mesencephalic, and the spinal reticular tracts. Spinal limbic one ends up in the cortex in the limbic lobe. Here we have the reticular formation in the midbrain, and then this is the collicula. So it's through those three pathways that we get our slow pain response. So how many tracks are we at right now? 2 for the conscious relay pathway, and then 3 for the divergent pathway. Oh, Carl says, ooh, okay, so good question, Carl. Some of them don't cross over. But, yeah, still 5, yeah. So think of it like they're going to cross over at the spinal cord, but because they're diverging, it kind of goes all over the place. That's the spinal thalamic tract, Classy. But because they're piggybacking on the pain pathways initially to get into the spinal cord, for this diagram, they made it so that they would all cross over. Because technically when you have shock or like pale or your whole body's anxious, it's bilateral. But for like the throbbing pain sensation, so some pain sensation, that would be crossed over. It just makes it easier. So you're right. So right now we have 5 pathways that we've talked about. The last ones is there's 4. Now we're going to be talking about one that's really, really important in terms of movement and learning motor skills. This is the unconscious relay pathways. They're called the unconscious relay pathways because they go into the cerebellum. For things to be conscious, where does that signal need to end up? For senses to be conscious, where would that occur in the cerebral cortex? The cerebrum, yeah. And where specifically, Hannah? Somatosensory area, yeah. So Talassi's saying the thalamus. Everything going in and out of the brain has to go through the thalamus. That's why the thalamus is like a 2 big circles right as the brainstem becomes the cortex, because everything going in and out has to go through there. It's the ultimate relay center. But these pathways don't end up in the cortex. They end up in the cerebellum. So their sense, the signal and that information is constantly being sent, but we're not consciously aware of it because it's not ending up in the somatosensory area. Yes. Conscious, first in terms of sensing, has to be somatosensory area. Are we okay with that, everyone? Promise? Yeah. Go Shane. Okay. So this is what my research is on, so it gets me super excited. So I'm going to nerd out a bit, but there's 2 types of information that get sent via the unconscious relay pathways. Information from the proprioceptive receptors in your body and activity in the spinal interneurons. Okay? So using the spinocerebellar tracts, this is what happens. Every time we were talking about proprioceptors, I forget who asked about alpha gamma coactivation. We have muscle spindles, Golgi tendon organs, and we have our joint receptors. That's going to be all providing proprioceptive information. That information, when it gets to the spinal cord, gets sent out, which is the divergent pathway, to the spinocerebellar tract. So all of the proprioceptive information in our body is constantly being monitored in real time by our cerebellum. It's not conscious because it's not going to the cerebral cortex. It's going to the cerebellum. So in real time, our cerebellum is constantly aware of how our whole body is positioned in space. Make sense? The second receptor that gets sent out is spinal activity from the interneurons. So if I was to, we were talking back to the motor planning lecture when we were talking about the different motor planning areas. Do you remember the primary motor cortex, supplementary motor cortex, and premotor cortex? They were the areas that sort of figured out what muscles to contract, and then it got sent down to the spinal cord. Then there would be a synapse from the upper motor neuron out to the lower motor neuron to the muscle, right? That synapse from the upper motor neuron that came from the brain to the lower motor neuron out to the muscle, that signal gets sent back up to the cerebellum via a spinocerebellar tract. So the second information the cerebellum is aware of is which muscles you're contracting. So in real time, your cerebellum is looking at how your body is positioned in space versus what muscles you're contracting. That's what it does. It just is coordinating in real time what's happening in terms of muscle activation and how your body's positioned. And it's through that process that our body is able to learn movements. What's the process of learning how to throw a baseball? Actual movement versus intended movement, correct. So if I am going to practice doing a motor skill, I'm going to keep practicing it and get a bit better every time because my coordination improves. Every time I get closer to the goal, my body tends to kind of remember, oh, I did it this way a little bit. So that's more towards the ultimate goal. It's through the repetition of doing it that we learn our coordination. It's because our cerebellum is unconsciously comparing intended movement, which muscles we contracted, versus what actually happened, our proprioceptive information. If we have issues with our cerebellum, we have uncoordination. That's called clinically ataxia. So there are 4 pathways in the unconscious relay pathway system that go from the spinal cord up to the cerebellum. The first 2 are the high fidelity pathways. So you're going to write down the posterior spinocerebellar pathway, to the cuneo-cerebellar pathway. And these represent the high fidelity pathway. High fidelity means like high definition. So this is coming from our proprioceptors. So, I don't know, can you guys see this? So under unconscious relay pathways, we're going to have 4. The first 2 are on the slide. The posterior spinocerebellar pathway and the cuneo-cerebellar pathway. This is proprioceptive information from the lower body, proprioceptive information from the upper body. Together, they make the high fidelity pathways that are for proprioceptive information going up to the cerebellum. The next 2 are internal feedback tracts. That's going to be information coming from what muscles we've contracted. So that's the anterior spinocerebellar tract. So that's going to be the muscle information from our lower body. And then we have our rostral spinocerebellar tract. That's going to be our muscle activation information from our upper body. Did we all write that down? An engram? Like a backwards forward sort of thing? So remember we were talking about Latin and how Latin helps us understand stuff? So spinal cerebellum, what would that mean in Latin? Spine to cerebellum. Can we all agree on that? Okay. Rostral means nose. So spinocerebellar tract, rostral spinocerebellar tract is like nose, spinocerebellar, so upper body, spinocerebellar tract. Here's that word cuneo again, just like fasciculus cuneatus. It's like a hand bone, cuneiforms. So the root word of that means hand. So the cuneocerebellar pathway is upper body to cerebellum. It will just help you sort of remember. Please know that these pathways, they remain ipsilateral. So because of the most evolutionarily newer ones, where we have before the cerebrum of the left side controlling the right side of the body and vice versa, the cerebellum, the pathways don't cross. Interesting, right? Or they not all cross. So if you had a problem with the left cerebellum, it's coordination of left body. Whereas with the cerebral cortex, it would be the opposite side. So these are the 7. Oh, sorry, 1, 2, 3, 8. Wait, am I screwing this up? Wow. These are the 9 pathways that we learned about today. Are we all okay with understanding what the unconscious relay pathways do? Where do they end up? Okay. And what, no right answer, but like help me understand how much you guys took from that part. What would be their purpose? These 2 pathways, coordination, right? And Talassi and Hannah, would we be consciously aware of the information from these tracks? And why is that? Yep, perfect. So we all get it. Yay. Yep. So let's review it. Okay. So now we I don't know, if you guys find this very interesting. I think it's great to sort of be able to understand the information. Well, no, so the thalamus is for everything going into the cortex. Yeah. Yeah. Because the thalamus is higher, so it wouldn't even reach that high. So now we have the 3 main pathways of where sensory information gets transmitted up to the brain. What were the 3 different pathways? Generalized pathways. Number 1, conscious relay pathways. Perfect. So what are the 2 conscious relay pathway tracks? Yep. Perfect. And the difference between those 2 pathways are the type of sensation that they provide and where that information crosses over from the left side to the right side of the body or vice versa. We had a question from Carl. How does the cerebellum use this information again? Like, where does it transmit the unconscious info? Ooh, so the unconscious info isn't really transmitted to the cortex, like to the primary somatosensory area. It affects the signal going down. So the primary motor cortex is going to send out a signal of what muscles to contract. And if through experience I've registered that this is the way I want to coordinate my muscles, it's going to alter the firing pattern of the muscles you sent out from the primary motor cortex. So think like the basal ganglia affects force. It's going to look at a activation of muscles and then alter it a little bit in force to make sure it's smooth. The cerebellum is looking at the order in which you're firing your muscles, and it's going to change the order based on what you've repeatedly learned through practice as the most efficient way. No, that would happen as that signal is getting crossed or passed down the brainstem. Let's verify that one here. Hold on. Right now, I think I heard the difference between the two is sensation and bilateral. No, they're both bilateral. It's where the crossing over is happening. Okay. Yeah. So, okay, so I'm standing, right? So let's say pain in my leg. Pain in my leg is going to come up to the spinal cord. That's neuron 1. Cross over and up. That's number 2. And then from the thalamus up to the part. Pain, right? Whereas the proprioception, so let's say it was fine touch, like someone's touching me in my hip. Oh, nice. But that's going to be sent up the spinal cord. That's the first neuron. Then crossover, second, or sorry, it would be here. Crossover, then to thalamus, then up. Just the location of the crossing. Okay. Both use 3 neurons to get from the receptor up to the brain. The second was what? The second group of pathways or tracks was what? Divergent. So Talassi, just the spinal thalamic tract and the conscious relay pathway, the spinal thalamic and dorsal column use 3 neurons. The divergent pathway uses way more than 3 because it's a signal that's going, one signal is going up and getting transmitted to different areas. Diverging signal. And so we had our spinal mesencephalic, our spinal reticular, and our spinal limbic tracts that are associated with slow pain. The medial divergent pathways are for the slow pain experience. So what would the spinal mesencephalic tract do? Yes, that's correct, Hannah. Spinal mesencephalic, what would that do? Yep. Or then turning your head towards pain. Yeah. Okay. Super simple. And that's because it goes from the spinal cord up to the colliculi that we learned about in the midbrain. Okay. What about the spinal reticular tract? What does that do? Okay, so if we have a slow pain experience using the spinal reticular tract, what's that going to do for our body? Yeah, like all of that sort of more like systemic responses to a very painful stimulus. Yeah, exactly. Okay, and then the last one is the spinal limbic tract. What does that do? The emotional response to pain. Perfect. Okay. The last one is the unconscious relay pathways. What is the purpose of those sensory pathways? Okay. And where do they end up? Receptor to cerebellum. Yep. We have our high fidelity tracks and our internal feedback tracks. What were the high fidelity tracks responsible for? You're right, Joseph, but which one? Proprioception, yep. And then the internal feedback tracks, which ones were those for? Muscles, right? Yeah, interneurons. So the cerebellum is constantly in real time aware of how our body's positioned via proprioceptive receptors and those cerebellar tracts, and then what muscles we're contracting via the interneurons and then those cerebellar tracts. So it's comparing actual versus intended movement. And it knows when doing something repeatedly, we are sort of changing our coordination, we're changing our activation patterns. And so the cerebellum is storing what is the best activation pattern for that movement. So when I decide I want to move, that information gets sent down from the primary motor cortex and those motor planning areas. And then as it gets sent down, the cerebellum registers, okay, we've done this move before. This is the order in which you should fire your muscles. That's how we develop coordination. Because when you are planning on throwing a baseball, you don't say to yourself, okay, I need to shoulder flexion, arm flexion, wrist flexion. Like you're not thinking about it. Your body works on goals, right? So that coordination is stored in our cerebellum, and it's through the use of the spinocerebellar tracts, the two. So in terms of movement, these are very, very important. So the rostrosinus, so Shane's asking again, so the anterior spinocerebellar and the rostrospinocerebellar tract are internal feedback tracts. So they're muscle activation information for the cerebellum from the lower and upper body. And then the high fidelity tracts are the posterior spinocerebellar and the cuneo-cerebellar tract. And that is going to be proprioceptive information from our lower and upper body. So, are we okay? Let me just show you this slide really quick. So now, if we can all look at this slide, see how we're formulating what each of the different tracks are? Now we know if the spinal cord is a bunch of just of wires, think of like HDMI cables and how they're all coordinated. Now we know more and more about how it's sort of put together in the white matter of our spinal cord. Here we have our dorsal column, fasciculus gracilis, fasciculus cuneatus. Look at the spinocerebellar tract here, spinocerebellar tract. There's the spinothalamic tract. And so we're developing a picture through this course of how the neurological system is put together and how it coordinates movement. How was that, everyone? Was it too much, or did I try to break it down pretty good? So I feel like, for this is still being recorded, so for all of you watching, if you break it down this way, I think it's easier to sort of get that information in. Remember, we're just talking about the 3 different pathways for sense and the different tracks associated with each of those pathways. Okay, awesome, great. I'm glad that's what I was trying to do. Work through it, and then we have the motor system and its pathways next class. Oh, and Jen, do the quiz. Ah, you did it, nice. Okay. Yeah, so this lecture and then the next one are going to be big into the next midterm because now we're finally putting everything together. The questions won't, I'm not trying to make trick questions, But I should quiz you guys on what I think is the most important in learning how to move, and based on our like health background and kinesiology background, that's what I want you to take from this course. Awesome. Have a good week, everyone. Just email me if you have any questions. Bye.